In this video, we're going to be taking a look at the integral test, and we'll be stating the integral test, the actual statement in a moment. But first off, we're going to look at a little bit of intuition about why the integral test works, how it works, and we're going to be looking at it for a convergent series. So the series that I want to start by considering is just the series 1 over n squared. So this is actually one of the ones we looked at in the last video. And I claimed it was convergent. We didn't actually talk about how we know that, but essentially it is going to be convergent. What are the terms being added up? It's 1 over 1 plus here. The second term would be 1 over 2 squared, to be 1 over 4. 1 over 3 squared is 1 over 9, 1 over 16, and so on. And this keeps going forever. This is going to be 1 over n squared. And what we want to do is we want to know the behavior. We want to know, is it going to be convergent or is it going to be divergent? And to do that, what we're going to do is consider something that we are more familiar with. We're going to take the corresponding function. So what's the function that corresponds to 1 over n squared? Well, that's going to be the function 1 over x squared. Okay, and if we take that function, what we're going to be looking at is we're going to look at the integral from 1 to infinity 1 over x squared. Okay, now why we care about this, you'll see in a moment, but this is nothing that is that new. This is an improper integral, and it's actually one that we've seen before. This improper integral is going to be the limit as t approaches infinity. Let's do this one quickly. So this is x to the minus 2 dx, and we can do our antiderivative. So we have here minus 1 over x from 1 to t, and if I plug everything in, I get here limit as t approaches infinity minus 1 over t minus 1. And this part here goes to 0, so the whole thing is just going to be equal to 1. Okay, in particular, it's convergent, but in this case, it actually goes to 1. All right, so that's fine. Now, why do we care about this? Well, let's actually take a look visually at what this integral represents. It represents the area, and it's the area underneath 1 over x squared from 1 to infinity. So here we have a graph of 1 over x squared, and we can tell the integral from 1 to infinity, that's going to be this area right here. And we know that that area converges. Okay, that area is finite. In other words, this function 1 over x squared, it approaches 0 fast enough as x goes to infinity that even though the base width is going to be getting infinitely large, we have that the height of the function is going to 0 fast enough to ensure that this one converges. That area is finite. Now, how does that help us here? Well, let's take a look at a few different rectangles, and these rectangles are going to be very familiar. They should remind you of rectangles we looked at very early on when we were going through Riemann sums. So the first one is starting here at x equal to 1. Let's build a rectangle using the height of the curve there. So we end up with a rectangle, and the base width here is 1. And the height is also going to be 1 if I plug it into my function. So this one here, it's going to have a base width of 1, height of 1. It has an area of 1. So that's fine. Now let's do the same thing. But let's do it here at 2. Okay. And if I do that, I go up, there's the height. And this time that is going to be my rectangle, and the area there will be 1 over 2 squared. It will be 1 over 4. And now you'll notice that is 1 over 4. That is the second term in our series, and you will also notice that this value of 1, that was the first term in our series, and this is not a coincidence. This is very much how we set this up. So now if I go to this third term and I find my third rectangle, I plug that into my function, I get 1 over 3 squared. The area of that rectangle is going to be 1 over 9, and that's going to be the third value. If I do this one more time, at 4, then my height continues to get smaller and smaller. The height there is 1 over 16, still has the same base width though of 1, so that one's going to be 1 over 16, and that's my fourth value. So what does this actually mean? We have our series from 1 to infinity, 1 over n squared. It can be written as 1 plus, in brackets, we have our first term is 1 over 4. Then we have our second term is going to be 1 over 9. And our third term is going to be 1 over 16, and so on. We could keep doing this, okay? But what is the point here is that if I focus on just this portion right here, okay, starting off at 1 over 4, that second rectangle, if I look at this area that we started with, this gray area right here, we know that that is the actual value of this integral. That's the area underneath the curve 1 over x squared from 1 to infinity. And we know that that area converges. We know that that area is equal to 1. And we also know that that gray area right here, all the way from 1 to infinity, that gray area has to be larger than the sum of all of these different rectangles that we're looking at right now. Okay, so that means that this sum is going to be smaller than 1. So if I carry this 1 forward, I can also put 1 plus here the integral from 1 to infinity of 1 over x squared. Okay, and this value has to be larger than the sum of all of these rectangles. And I also know that this right here, this integral is just equal to 1. So that's going to be 1 plus 1 is equal to 2. And so in other words, what we have is that our series, 1 over n squared, we don't really know right now yet if it converges or diverges, but it definitely must be less than or equal to 2. Okay, and so here what we have shown is that we have our integral 1 over x squared. It is convergent, and really if you put this together with the fact that these terms in our series, they are all positive, they are decreasing, okay, and this function doesn't have any discontinuities in it, all right. Putting all of this together does actually ensure then that this series has to converge, okay? This series is not going to be able to grow without bound, okay? We verified that by saying that it is smaller than the area underneath 1 over x squared. And it also is not going to have any erratic sort of values bouncing back and forth because the terms are all positive and the terms are all going to 0. Okay, so in the next step, we're going to be looking at what the formal statement is of the integral test. But this is sort of the idea behind the integral test, is that if you start off with a convergent integral and you are trying to talk about the corresponding series, then the integral and the series are going to have the same behavior. Okay, and then similarly, you can do this for divergent ones as well. Okay, and the intuition is very similar, but the setup for this part would be a little bit different. Okay, we're not going to get into that, but it will still be stated as part of the integral test. So here we have the actual integral test, and you will notice it says essentially what we were going through before, except that it has 3 conditions here on our function. So the function needs to be continuous, it needs to be positive, and it needs to be decreasing in order for the integral test to apply. So it's continuous, positive, decreasing on the interval from 1 to infinity, and we're going to let an be equal to f of n. Now this is a weird way of stating really that we're going to consider the corresponding function and series. Okay, so in the last one we had the series of 1 over n squared, and the function that corresponded to that was 1 over x squared. That's all that is meant by this an equal to fn statement. So if we have all of this set up, then what does the actual integral test say? Well, it says that really the series and the integral are going to have the same behavior. So if your series is convergent, then, if your integral is convergent, then your series is also going to be convergent. And it says that here, if your integral is divergent, then your series will similarly be divergent. So really, it is saying that the series an from 1 to infinity and your integral from 1 to infinity, that they have the same behavior. They are either both convergent or they are both divergent. They converge together or they diverge together. So here, let's take a look now at sort of how we would use the integral test. So here we have the series 1 over n squared plus 1, and we're going to be testing it for convergence or divergence. So you can tell right away by looking at it, it's not a geometric series, okay? It has no terms that look sort of like exponentials. It's also not possible to, split it up into partial fraction decomposition, and so maybe get a telescoping series. And in this case, we can try the nth term test. Okay, we can check here the nth term test. What we're really doing is looking at the limit as n goes to infinity of an, and really, normally I would just do this sort of in my head. Okay, you don't need to write this down because it's going to be clear here in a moment that this limit is going to be 0. And if you think about it for a second, the nth term test says that if that limit is 0, that's unfortunate because then the test fails. Okay, the test is inconclusive. So for us, the nth term test is not going to work. Instead, what we're going to be doing here is using the integral test. Okay, now for the integral test to work, okay, we need to have that our function, and in this case the corresponding function would be 1 over x squared plus 1, but it needs to be three things. First off, it has to be continuous. So here f of x is actually going to be continuous on all real numbers. Okay, this denominator is never 0. There's never any vertical asymptotes. It's continuous on r. Okay, now the second thing that we're going to want to be looking at is it positive? Well, yes, f of x here is always going to be larger than 0. Again, on all real numbers, that's going to be true. And the third thing is we want to check, is it increasing or is it decreasing? Because we need it to be decreasing. Well, how do you verify whether a function is decreasing or not? Well, in Cal 1, you will have learned to look at the derivative. The derivative in this case is going to tell us directly that this function is decreasing. So here f prime is going to be equal to, so remember our function is really x squared plus 1 to the minus 1. So it's going to be negative x squared plus 1 to the negative 2. Multiplied here, we do a little bit of a chain rule, and we're going to multiply it by 2x. So we get negative 2x divided by x squared plus 1 to the power of 2. And now we want to know, is that derivative going to be positive or is it going to be negative? And remember that we're looking at values here that need to be in the interval from 1 to positive infinity. We're only looking at positive values of x. So here, if I look at the denominator is always going to be positive, but I do have this negative term in the numerator, and I have this x in the numerator. And really, the result of this is that if x is positive, then this whole thing is going to be negative. So this is going to be less than 0 as long as x is in the interval from 1 to infinity. And that means that our function is going to be decreasing. Okay, so we can write that in here. So therefore, f of x is decreasing on the interval from 1 to infinity, and that's perfect. So now that we have all three of those conditions satisfied, we can actually go and check what is the behavior of our integral 1 over x squared plus 1. And so here we can set this up as an improper integral, t approaching infinity, 1 to t. What is the antiderivative of 1 over x squared plus 1? So for this one, you need to realize that this is going to give us arctan of x, and we're going to evaluate that from 1 to t. So that's going to give us the limit as t approaches infinity of arctan of t minus arctan of 1. And what does this give us? Well, we have that arctan of 1 is going to be equal to root 2 over 2, and we have arctan of t as t approaches infinity. We're looking at the arctan function as its input goes to infinity, and really that arctan function is just going to approach pi over 2. Okay, it has that horizontal asymptote at pi over 2. So this whole limit now is going to be equal to pi over 2 minus root 2 over 2, and really that means it is a limit that exists, which means that the integral is going to be convergent. Okay, so that's fine, the integral converges, but what does that mean about our series? Well, it means that because of the integral test, our series must also have the same behavior. Our series must also converge. So therefore, the series 1 over n squared plus 1 must also converge by the integral test. Okay, so we know the behavior, it must converge. Now, the one last question that I want you to consider is, what does this series equal to? Okay, if we know that it is convergent, what is that series going to be equal to? And the temptation here is to think that maybe that series is going to be equal to this number, right? Maybe it's going to be exactly equal to the integral from 1 to infinity and what that integral converged to. And this is absolutely not the case. Okay, remember that in the last example, we had that our function, okay, was bounding all of these squares underneath of it, but it was definitely not the same value, okay? Those two areas were drastically different from each other, okay? So here we get that they have the same behavior, but it is by no means going to have the same value. It's not going to be equal to the same thing. And in fact, we do not know, and we have no way of knowing right now what this series is actually going to be equal to. So we will just leave it as is. We just know that it must converge. Okay? So that's how we can go using the integral test. Really remember that you have these three restrictions. You have to verify that you have continuity, you have to verify your function is positive, and you have to also show that your function is decreasing on the interval from 1 to infinity. And really, yes, we have those three conditions. I'd say really there's sort of a fourth condition. The fourth condition is that you need to be able to do that antiderivative. If you don't know how to do the antiderivative, then there's no reason to even think about doing the integral test. Okay, so remember that you can't always use the integral test, and even when you can, it's going to take a little bit of time. Okay, there's quite a lot of work in here. And actually, there's a lot of work in here compared to the other tests. So often you'll sort of use it when the other tests are not working. Okay, so that's it for the integral test. In the next video, what we'll be looking at are p-series. And p-series is going to remind you very much of what we have seen before with a p-integral. Okay, so we know by looking at integrals when this integral is going to converge or diverge based on the value of p. Well, now we want to talk about very much the same thing, but we're going to be looking here at a series and these are the p-series. We want to know when the p-series converges or diverges, and now that we have the integral test, we can link the two together, okay, and that's exactly what we're going to do.